Theorem: if M is a closed linear subspace of a normed linear space N, show that the quotient space N over M with a suitable norm is also a normed linear space. Proof: we first finally verify all the postulates for a norm. First, norm x plus m is greater than or equal to 0 since norm is a non-negative. For norm x plus small m is greater than 0 for every set of non-negative real numbers is bounded below, and so infimum norms x plus small m such that small m belongs to capital M exist and is a non-negative. Second, to show that norms x plus m equals to 0 employs both ways. X plus m equals to 0 element of n over m. Let x plus m equals to m implies x belongs to m. Hence, norms x plus m equals to infimum of norms x plus small m such that x and small m belongs to capital M equals to infimum norms y such that y equals to x plus m belongs to capital M equals to infimum norms y such that y belongs to M equals to 0, because M being a subspace contains 0 vector whose norm is a real number is 0. Finally, x plus m equals to m implies norms x plus m equals to 0. Conversely, suppose that norms x plus m equals to 0, so infimum of norms x plus small m such that small m belongs to capital M equals to 0 implies there exists a sequence mk in M such that norms x plus mk tends to 0 as k tends to infinity. Therefore, limit k tend to infinity mk equals to minus x. But M is closed and sequence mk is a convergent sequence in M converging to minus x. So minus x belongs to M implies that x belongs to M as M is a subspace. Thus, norms x plus m equals to 0 implies x belongs to M, which implies x plus m equals to M. Third, to prove norms x plus m plus y plus m is less than or equal to norms x plus m plus norms y plus m. Norms x plus m plus y plus m equals to norms x plus y plus m by the definition of addition of coset equals to infimum norms x plus y plus small m such that small m belongs to capital M equals to infimum of norms x plus y plus small m dash such that m small m and small m dash belongs to capital M, because m small m plus small m dash belongs to M, which implies small m and small m dash belongs to capital M as M is a subspace, equals to infimum of norms x plus m plus y plus m dash such that small m and small m dash belongs to M, which is less than or equal to infimum of norms x plus m plus norms y plus m dash such that small m and small m dash belongs to capital M, because norms x plus y is less than norms x norms y norms x plus norms y in N. So infimum norms x plus m such that small m belongs to capital M, plus infimum norms y plus m small m dash such that m dash small m dash belongs to capital M, equals to norms x plus m plus norms y plus m, which shows that the triangle inequality hold. Fourth, to prove that norms alpha into x plus m equals to modulus alpha into norms x plus m. Norms alpha into x plus m equals to infimum of norms alpha into x plus small m such that small m belongs to capital M, equals to infimum of modulus alpha into norms x plus small m such that small m belongs to M, because norms alpha into x equals to modulus alpha into norms x equals to modulus alpha into infimum of norms x plus small m such that small m belongs to capital M, equals to modulus alpha into norms x plus m. And so the absolute homogeneity of the norm is introduced is true. It follows therefore that n over m is a normed linear space. We now prove that if n is complete, then so is n over m. We know that a Cauchy's sequence is a convergent if and only if it has a convergent subsequence. Let a sequence xn plus m be a subsequence of the original Cauchy's sequence in n over m such that norms x1 plus m minus x2 plus m is less than 1 upon 2, norms x2 plus m minus x3 plus m is less than 1 upon 2 square, and so on. And in general we have norms xn plus m minus xn plus 1 plus m is less than 1 upon 2 raised to power n. We prove that the sequence is a convergent in n over m. Choosing a vector y1 in x1 plus m and selecting y2 in x2 plus m such that norms y1 minus y2 is less than 1 upon 2. Now choosing a vector y3 in x3 plus m such that norms y2 minus y3 is less than 1 upon 2 square. Continuing this way, we obtain a sequence yn in n such that norms yn minus yn plus 1 is less than 1 upon 2n. If m is less than n, then norms ym minus yn equals to norms ym minus ym plus 1 plus ym plus 1 minus ym plus 2 plus so on plus yn minus 1 minus yn less than equal to norms ym minus ym plus 1 plus norms ym plus 1 y minus ym plus 2 plus so on plus norms yn minus 1 minus yn less than equal to 1 upon 2 raised to power m plus 1 upon 2 raised to power m plus 1 plus so on plus 1 upon 2 raised to power n minus 1 less than 1 upon 2 raised to power m plus 1 upon 2 raised to power m plus 1 plus so on plus 1 upon 2 raised to power n minus 1 plus so on equals to 1 upon 2 raised to power m upon 1 minus 1 upon 2 equals to 1 upon 2 raised to power m minus 1. So because 1 upon 2 raised to power m plus 1 upon m plus 1 1 upon 2 raised to power m plus 1 plus so on is a GP series, and s raised to power infinity equals to a upon 1 minus r. So norms ym minus yn is less than 1 upon 2 raised to power m minus 1. Therefore sequence yn is a Cauchy's sequence in n. Since n is a complete, there exists a vector y in n such that yn tends to y. Finally, we prove that xn plus m tends to y plus m belongs to n over m. We have norms xn plus m minus y plus m equals to norms xn minus y plus m equals to infimum of norms xn minus y plus small m such that small m belongs to capital M is less than equal to norms xn plus small m minus y for all values of small m belongs to m, which is less than equal to norms yn minus y tends to 0 as yn tends to y. Hence xn plus m tends to y plus m belongs to n over m, and consequently n over m is complete.